Hello, welcome. In this lesson, we are going to talk about finite sets and infinite sets, and also countable sets and uncountable sets. For example, let's consider two sets, A with elements 2, 4, 6, 8, and B with elements 3, 7, 11, and 13. We see both sets have the same number of elements, namely 4. We discovered this by counting the number of elements in each of the two sets. Alternatively, we can reach the same conclusion without counting by simply pairing up the elements. For example, we have the elements from set A and here the elements from set B. We can make a pair like this. 2 is paired up with 3 from B, and 4 from A is paired up with 7 in B, and so on. Or like this way. 2 can be paired with 7, 4 can be paired with 13, 6 can be paired up with 11, and 8 can be paired up with 3. For infinite sets, the concept of two sets being of same size or having the same number of elements is vague. For example, let S denote the squares of the positive integers. We see that the set S is a proper subset of the positive integers n. Galileo observed that the sets S and the set of natural numbers 1, 2, 3, 4, 5, and so on can be placed into a one-to-one correspondence as follows. So the element 1 from the set of natural numbers is paired up with 1 squared, and 2 is paired up with 2 squared, and 3 is paired up with 3 squared, and so on. This example caused Galileo and many subsequent mathematicians to conclude that the standard notion of size of a set did not apply to infinite sets. Cantor, on the other hand, realized that the concept of one-to-one correspondence raised many interesting questions about the theory of infinite sets. In this section, we take a closer look at infinite sets and what it means for an infinite set to be countable. Let's begin our discussion with the definition of equivalent sets. Two sets A and B are said to be equivalent or to have same cardinality, denoted by this symbol, if there exists a one-to-one function from A onto B. Simply, if there exists a bijection from A onto B. Consider an example. Let A and B are the previous two sets, then A is equivalent to B, since there exists a one-to-one function f from A onto B, as shown here. The notion of equivalence of sets satisfies the following. A set A is equivalent to itself. This property is called the reflexive property because there exists a map from A onto A, which is called the identity mapping, defined by I at A equals A for all A in the set A. So it takes an element from A, the set, and produces an element in the set A. And this identity mapping is one-to-one and onto. So every set A is equivalent to itself. 2. If a set A is equivalent to the set B, then the set B is also equivalent to the set A. This property is called the symmetric property. If A is equivalent to B, then there exists a function f from A onto B. Then there exists an inverse function of f from B into A, which is one-to-one and onto. Therefore, B is also equivalent to A. Property 3. If a set A is equivalent to the set B and the set B is equivalent to the set C, then the set A is equivalent to the set C. This property is called the transitive property. So we can illustrate with the following diagram. The set A to B, there is a one-to-one and onto map F. And from the set B to set C, there is another one-to-one and onto map G. Then there exists a map from the set A to the set C, which is called G of F. And we can show if F is one-to-one, G is one-to-one, then G of F is also a one-to-one map. Similarly, if F is onto and G is onto, then G of F is also an onto map. Simply, if F and G are two bijections, then G of F is also a bijection. Therefore, the set A is equivalent to the set C. For each positive integer n, let n sub n denotes this set. The set of positive integers from 1 up to n. For example, n4 would be the set of positive integers from 1 to up to 4. If A is a set, we say A is finite if A is equivalent to n sub n for some n, or if A is empty set. B, we say A is infinite if A is not finite. C, a set A is called countable if A is equivalent to the set of positive integers. D, the set A is called uncountable if A is neither finite nor countable. The set A is called at most countable if A is either finite or countable. Countable sets are also called denumerable or innumerable. Let's consider some examples. As before, let S be the set of all the squares of the positive integers. The function g from S to the set of natural numbers defined by this formula, g of n equals square root of n, is one-to-one mapping from the set S onto the set of natural numbers. Please verify this. Thus, the set S is equivalent to the set of natural numbers. Thus, the set S is countable by definition. Let's consider another example. the set of integers z is countable. To see this, consider the function f from the set of natural numbers to the set of integers, defined by this formula. F of n equals n over 2 if n is even, and f of n equals negative of n minus 1 over 2 if n is odd. For example, f of 1 would be, since 1 is odd, we have minus of 1 minus 1 over 2, which is simply 0. F of 2 equals, since 2 is even, we have 2 over 2, which is 1. F of 3, since 3 is odd, we have negative of 3 minus 1 over 2, which is negative 1, and so on. This is a one-to-one function from the set of natural numbers onto the set of integers. Thus, the set of natural numbers is equivalent to the set of integers. And by reflexivity, the set of integers is also equivalent to the set of natural numbers. Hence, z is countable. This is illustrated in the following figure. For example, the element 1 goes to the element 0, the element 2 goes to the element 1, the element 3 is mapped to negative 1, the element 4 is mapped to 2, and so on. Every natural number gets mapped to some element in the set of integers, and every integer in the set z is an image of some element in the set of natural numbers. So please verify that this map is one-to-one, and this is onto also. Theorem. The Cartesian product of the set of natural numbers with itself is countable. Let's see the proof of this theorem. Recall that the Cartesian product of n with n is a set of all pairs like this, m comma n, where m and n are both natural numbers. For example, this set n cross n contains a pair like 1 comma 1, 1 comma 2, 1 comma 3, and so on. So 2 comma 1, 2 comma 2, 2 comma 3, so on, 3 comma 1, 10 comma 10, 10 comma 11, so on. Every possible pairs of this form, where the first number in the slot is a natural number and the second element in the slot is also a natural number. Now we consider a function f from the Cartesian product n cross n to the set of natural numbers defined by this formula. So f of m comma n equals 2 to the m minus 1 times 2n minus 1. For example, f of 1 comma 3 would be 2 to the 0 times 6 minus 1, which gives us 5. Similarly, f of 3 comma 2 gives us 2 squared, 2 to the 3 minus 1 times 4 minus 1, and this gives us 4 times 3, which is 12, so on. Now it can be shown that the map f is a one-to-one function from n cross n onto n. So it's a one-to-one and onto map. To show this, let f of m1 comma n1 equals f of m2 comma n2. If the outputs are same, we need to show the pairs are also same. m1 comma n1 must be equal to m2 comma n2. Now, the left-hand side gives 2 to the m1 minus 1 times 2n1 minus 1. And the right-hand side gives 2 to the m2 minus 1 times 2n2 minus 1. Now, if we transpose this term, this factor, to the left-hand side, we obtain this factor, 2 to the m1 minus m2. And we have the other two factors as it was in the previous equation. So this is equation 1. Now, equation 1 is true if m1 equals m2. Otherwise, the left-hand side is even, because this is if m1 is not equal m2, then this would be some factor of 2 times some integer. So the left-hand side must be 2 times of some integer. So it's an even number, whereas the right-hand side is an odd integer. So they can be equal. So we must have m1 equals m2. And for that case, this factor would be 2 to the 0. And we would have an odd integer in the left-hand side, so as in the right-hand side. So if m1 equals m2, we would have 2n1 minus 1 equals 2n2 minus 1. Then by cancelling negative 1s from both sides and then 2s from both sides, we are having n1 equals n2. So this proves that f of m1 comma n1 equals f of m2 comma n2 implies that m1 comma n1 must be equal to m2 comma n2. Hence, f is 1 to 1. Similarly, we can show that f is onto. Please try to prove it. Corollary. If A and B are two countable sets, then their Cartesian product, A cross B, is also countable. Let's have a look at the proof. Since A is countable, therefore A is equivalent to the set of the natural numbers. Similarly, since B is countable, B is also equivalent to the set of natural numbers. Then there exist maps f and g from A onto n and B onto n respectively, such that for A and B in the set of natural numbers, f of A equals some positive integer and g of B is also some positive integer. Call them n sub A and n sub B. Since f and g are maps from A onto n and B onto n. Now we define another map H from the Cartesian product A cross B to the Cartesian product of n with itself, such that H of A comma B equals n sub A comma n sub B. Now we can also show H is also a one-to-one map from A cross B onto n cross n. Then A cross B is equivalent to the set n cross n. And by the theorem 3.2.1, n cross n was equivalent to n. Therefore, by the transitivity, A cross B is equivalent to the set n. So observe once again, A cross B is equivalent to n cross n, and n cross n is equivalent to n. So by transitivity, A cross B is countable.